Hello, everyone. Um, the purpose of this video is to talk about the uniform distribution of death principle that's used in actuarial science, and to use that principle to find a formula that relates the present value of a whole life insurance policy that pays at the end of the year of death versus the hypothetical whole life insurance policy that pays at the exact time of death. In other words, a curve-tape model in a year of death versus the continuous model. So let's get started. And let's get this. And we're going to go ahead and start. And with the genesis of this video here this is a part of a text from Dixon, Hardy, and Waters, Actuarial Mathematics for Life Contingent Risks, 3rd edition. And we see this particular passage of text here. It starts with the definition of the expected present value of a life insurance policy that pays at the exact time of death. And through breaking this down, we end up with, now technically speaking, from here to there, it's no longer equality, but that's all right. We end up right here comparing the present value of the life insurance policy that pays at the exact time of death, as you can tell by the decoration of the overline, versus one that pays at the end of year of death. Now you can see this is rather terse, so we're going to go ahead and fill in the details here. So the very first thing I want to mention is that this is using the uniform distribution of deaths, and it makes this approximation here. So I want to give a very super brief review because this is something actuary students have to know, but if you're just learning it for the first time, it might be difficult to hold in your mind these concepts throughout. So let's go ahead and let's recall what that means. Now, the uniform distribution of deaths, how it was presented in the text, and this is basically what this means, is that if you, let's say, you wish to calculate survival, and the example I used here, you have a life that's aged 39.5 years, and you wish to calculate what the probability that life survives another 0.3 years using the uniform distributions of deaths. Now, what that assumption really means is that if you have a life aged X and you want to go to X plus 1, well, by the mortality models, you know the probability of death in that period is denoted by Q sub X. And, the idea is that you have lives that, die throughout this period. And what this assumes is that, let's say you have a set number, let's say L sub X, a set number of lives here, and you'll have fewer of them up here, that if you, the total number of deaths, which is basically the difference in the number of lives you have at the start of the period versus the number of lives you have at the end of the period, that these deaths are distributed uniformly throughout this interval. Now, in probability statistics it means that this distribution is uniform over 0, 1. And what that means is that over any period of time, let's call it delta t, the amount of deaths over this delta t is going to be the same here as it would be here, as it would be here for the same delta t. So the deaths are distributed uniformly. Now, because, well, what you'll find out is that means that the force of mortality is increasing. And it takes a little bit of time to figure out why that is, but let's just go ahead and do this example. Now, this, by definition, this is going to be the number of lives, 39.5. It's going to be 39.8. divided by lives of 39.5. But using the data that I have in this simplified example, and what I did is I went to the table at the back of the book and just threw away the decimals. This will be lives 39. 39. Now this is 0.8. That means the number of deaths that occur in this from 39 to 39.8 will be 0.8 times the total number of deaths that occur the 39th year. But the denominator, remember, we're starting at 39.5. So you start at lives 39 and you go half the distance. And using these hypothetical numbers here, which are not that far off, it's 99387. And I went ahead and just calculated the number of deaths here. So it's 0.8 times 49. And the bottom is 99387. And that's half a year. And, we'll go ahead and work that out just for completeness. So the numerator, my calculations are correct. That's just 99341 divided by the bottom, which is 387 minus 0.5 times 49. All right. And we get, as expected, 0.99979. And let's round up to 2. And you would expect this for life age 39. So this is also a quite realistic answer. I think it's always good to check that out. All right, so that's what uniform distribution of deaths is. But how does it relate here? Well, how it relates here is, remember, the density function. One way to write the density function for survival, or I'm sorry, for mortality, the density function, which is denoted like this, is written as probability of survival of life age x to t times the force of mortality. But we also know from definition, and I'm going to use the number s here just for a second, we also know this is going to be the negative of the derivative of the survival. So divide it, and with respect to s, my bad, times, divided by the survival. But remembering that this survival is just going to be 1 minus mortality. Darn it. It's supposed to be a Q. I know that. That's going to be, now, if you take the derivative of both sides, obviously the derivative of this is going to have the negative in front of it. So it cancels that negative and we get this. And that's an S. Okay, but under uniform deaths, uniform distributions of deaths, what that says is that the probability of mortality, and I'm assuming now S is strictly less than 1 and greater than equal to 0. So over that year, and I screwed that up again. This is supposed to be Q. Under the uniform distribution of deaths, so I got that right, is just going to be S multiplied by the mortality of a life age Q in the next year. So this S here is a subscript. This is a S times that. So now doing a little bit of calculus, all calculus students know that if you differentiate this with respect to s times qx, that's just going to be qx. All that is the derivative of m times x is just m, nothing more than that. So what it has to do with this means under UDD, the mortality is going to be this divided by the survival. So that brings us to the result we are looking for some mortality times this. Remember, this is now the density function. It's just that. And this, remember, is valid between s and f for s between 0 and 1. That's important right here. Obviously, this does not work over a long period of time, but this is a decent approximation for 1-year increments. That's important. So that is the uniform UDD assumption. So let's, and I was a little bit amiss here. That should be approximately equal to. Okay. Now let's keep that in mind. Now let's go to our what we're after. So, and we're going, well, this might be white enough, maybe not. Let's just make it a little wider. There we go. There it is. All right, so make this a little wider, and now let's get to our task at hand. So this is now what we wish to start with. Remember, we want to relate this to this. Remember, this is in the year of death. This is at the exact time of death. And so you should know why this is always going to be less than that. And the reason is that the payments are later in this model here. You pay at the end of year of death. Here you pay at the exact time of death. So we should keep that in mind. So let's start off with this. And by using the definition, we integrate from 0 to infinity. We have our force of interest. I mean, our, not force of interest, but our discount factor. And then we have our density function. And our density function, remember, is this. Starting at life age x, you start the force of mortality at x and let it vary beyond x. So that is our first thing. Now, the next thing it's going to be convenient to do, we're going to use the uniform distribution of death property. And so what we can do is we want to break this down into 1-year increments because that's when that applies. And we add the second one. And I forgot my DT here. Plus the third one, etc. etc. And so, okay. So what we now do is we can write this in summation notation. We can sum this starting at k equals 0 to infinity. And we're now going to integrate. We're going to integrate to k, from k to k plus 1. Okay. And we're still integrating the same thing, but we're integrating these separately. And you can assume interchanging of integration and summation, although that's not going to strictly be that problematic here. What I'm going to do is I'm going to take this. Yeah, I guess that's what I'm doing here. But let's let's do something with this. Well, we're actually not integrating a summation, so we're fine. We assume appropriate convergence and all that other rot. Now, let's take a look at this each integral for values of k. Well, let's take a look at that integral there. We're going to do something with each integral here. Now, this integral, I want to do a few things. And this is and so we can apply the uniform distribution of depths. Notice these are 1-year increments. So I'm going to do a substitution, okay? And the substitution I'm going to do is I'm going to let S equal T minus K, that is S plus K is equal to T. So then when T is K, S is 0. And when T equals K plus 1, S is 1. So this is now equal to the interval from 0 to 1. Now let's look at this V here. This is now Vs plus K. This right here is the probability of X. Remember now, this is 2S plus K. This is now mu sub X plus K plus S dt, okay? So we now have an integral from 0 to 1. Now what I'm going to take here, so far we haven't used the UDD yet. What I am going to do is I'm going to erase this a little bit right here. And I'm going to start pulling things on the outside when I can. Notice this K can come out. And what I'm going to do, in fact, I'm going to do one better than that. I'm going to move this over and I'm going to put a K plus 1 here. Now there's a reason I'm doing that. Well, then this becomes Vs minus 1, which is fine. Now this thing right here, I'm going to write this as, I'm going to go from X to K. Then go from, this is now going to be X plus K to S, right? So this cannot be taken out, but this can. And this thing right here, I have as U X plus K plus S. And that's a ds here, not bad. Now, I put my equal on this side. Now notice what we have here. I'm going to take this outside the integral sign because there's no S in it. So we have this. So that's outside the integral sign. Now this part right here, this is where we're going to use the uniform distribution of depths. That, of course, is a density function from S going from 0 to 1. And that, by definition, we said is going to be Q of X plus K. So replacing that is the uniform distribution of depths assumption. Because remember, we went through that. Now this does vary by K, right? So we can now, so this is not, from here to here is actually an approximation. So I should actually get rid of that. Now let's take this outside. This should look very familiar. And this is now the integral from 0 to 1, this very simple integral right here. Now I'm going to make it a little bit of an assumption here. Remember, V is a 1 over 1 plus I, okay? And so we also know that delta is a natural log of 1 plus I. So V is really e to the minus delta, where that's a force of interest. So this here, and that makes the integral a little bit simpler to wrap your head around. It's not a difficult integral, of course. This is now going to be e to the delta 1 minus s. And now we're at a calculus 1 integral that we can easily do. Oh, and I forgot my cubes. Ah, darn it. Remember, that's for each thing a k. So I probably should erase this right here. And this is correct, but I forgot to add this factor here. So let's do that now. Let's fix that. And now we have this integral here. So this integral, I'm going to write this down as e to the delta 1 minus s. Now that's just a calculus 1 integral that anyone can do. And watch me blow it. So it's going to be minus e to the delta 1 minus s divided by delta evaluated between 0 and 1. And it's just a lot of copying at this point. Now, if you plug in a 1, you get this. So you get a minus 1 over delta plus plugging in 0. E to the delta over delta, right? And I'll go ahead and I got one more thing to write. Equals, we got this. Now this thing, e to the delta, remember, is 1 plus I. So we get 1 plus I minus 1 over delta. And we get finally our finally glorious answer. We got that. And that's as simplified as we want to take it. Now let's go back and remember what we did. Remember that all the blue stuff was in this blue box, right? So so what I'm going to do is I'm going to take this and I'm going to take its infinite. What we just calculated goes in this blue box here. So what we actually have, and let's just write the actual formula here. What we actually have is approximately equal to the sum from k equals 0 to infinity, v, this, times I over delta for each term. But if we take this out, we're almost done. And now we have this. And what's this? This is the expected present value of a policy that pays at the end of year of death. And that's what we're after. So we actually developed the following approximation. Or an easy way to remember that is this. And I should say, and I shouldn't use equal here. I ought to use approximately equal to. That's approximately equal to. And so I should say, no, I have not done this in this notes here. But we also have, if you wish to go periods of M, which pays at the end of the nth period of death, we, by very similar means, we actually have this, which leads to the associated approximation. Again, I have not gone through this one. Oops, I screwed that up. Didn't want that. Where I raised to the I superscript M is nominal interest rate right here. Which is another approximation, assuming the uniform distribution of deaths. So that's what I wanted to talk about, and thanks for watching.